All right, we are on chapter 11, lesson 2. So this one is about the gas laws. Okay, so there are 4 gas laws. 3 of them are named after people. And then the 4th one is called the combined gas law, and it combines all 3 of these laws and relates them together in one. So if you're only going to memorize one, I would go with the combined gas law. Okay, today we're only covering 2 of them. We're going to look at Boyle's law and Charles's law. Okay, so I am just going to start with my phone, sharing the screen from my phone. We're just going to fill stuff in. So on your notes, maybe it does not want to take my fingerprint today. Huh, weird. All right, so of course it's going to take me forever. So that I don't have to flip back and forth, because on your notes, the only part that I can do from the PowerPoint really is like the definition of Boyle's law and Charles's law. So instead of doing that, we will just write them in here. Okay. All right, so Boyle's law. According to Boyle's law, the gas volume and pressure are indirectly proportional. Okay. So that means if you like double the pressure, as long as you keep the temperature constant, if you double the pressure, then the volume is going to reduce by half. Okay, so if you were to graph that, I'm going to come over here and draw a little bit of axes. Okay, so you put volume on your y-axis and pressure, not temperature, pressure on your y-axis, no x, good grief. Okay, you end up with a graph that would look like this. Okay. We can relate this mathematically. We can write it out as an equation. And we say P1 V1, so the pressure times the volume initially or at one time is equal to P2 V2, the pressure times the volume at some other time. Okay, so under the initial conditions versus a second set of conditions, basically. Okay, so sample problem. We have oxygen gas with a volume of 150 milliliters and a pressure of 947. So here's my V1 and my P1. Okay. Then it asks me to find what will the volume be. So that's going to be V2, right? It's a big old question mark. If the pressure P2 is 0.987 atmospheres. Okay, so I don't change my pressure very much. So let's see what that does to the volume. Okay, so it is important that we note that the temperature is constant here. Okay, so Boyle's law only describes at a constant temperature. So P1 V1 is equal to P2 V2, right? P1 V1 is equal to P2 V2. So I'm going to multiply 0.947 times the volume, 150 milliliters. It does not matter that my volume is in milliliters rather than liters. Solve for it in whatever it's giving you, but pay attention to the question if it asks you to convert that to something else. So it could say, what is the volume in liters? And then you would have to convert your milliliters to liters. Okay, but that's not what we're having to do here. So this is equal to 0.987 times V2. So I would multiply 0.947 times 150, and then rearranging this, I'm going to divide that answer by the 0.987. Okay. So if you were to write this out, you'd do 0.947 times the 150 and divide that by 0.987 to find V2. Okay. So when you do that, you would find that the new volume of oxygen is 144 milliliters. Okay, so you'd write your answer out as 144 milliliters of O2. Okay, and you do kind of need the whole thing to be totally correct, right? Because you got to have your units. Okay, so this is not a very difficult equation. The hard part comes in as we learn more and more of them, and then I just give you problems and I don't tell you which law you have to apply. That's where people start to mess up because they start just calling things random stuff. This is where knowing your units comes in, okay? And paying attention to the question, plugging in your values in the correct place. All right, so we're gonna do one more together, and then I'm gonna ask you to pause the video and try the last one on your own. So here we have the piston of an internal combustion engine compressing 450 milliliters of gas. The final pressure is 15 times greater than the initial pressure. We want to know the final volume of the gas, okay? So we're finding V2 again. So for this one, this is a little bit tricky if you're like, oh, I don't know what to do here, right? Okay. So my initial volume is the 450, and then I have some pressure. I'm just going to call it X. Okay, so whatever my pressure is, I'm just going to name it X, right? So that's P1. The final pressure is 15 times greater than that. So 15X is my final pressure, and I am looking for V2. Okay. So I should be able to say X times V1. I'm going to put 450X because that's what we do in math, right? 450 times X is going to be equal to my new volume times 15X. Okay, we don't have enough information, but we're actually fine. Because if we are solving for V2, not X, right? We're going to divide both sides by 15X. So I have 450X divided by 15X. So the X goes away. Okay, and then it goes way over here. So I just need 450 over 15 is equal to V2. So my new volume is going to be equal to about 30 milliliters. Okay, so that one was a little bit of a brain twister. That's why I did it as a problem I worked with you. So if you see another one that's kind of like that, then that's what you should be doing. Just treat the value as, call it a variable, but it's going to divide out. So treat it as its own thing. All right, this is where you should pause. And try this one on your own. So we have a helium balloon. Here's V1 at this pressure P1. We're going to find V2, what volume? Ooh, at standard pressure. So P2 is 1 atmosphere. You have to know what standard temperature and pressure are for this. So remember, standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. Because I was given this in atmospheres, this works out fine. If I had been given the pressure in some other units, I would have to convert my 1 atmosphere to those units, which isn't that hard because it's either going to be millimeters of mercury, where it's 760, or 101.3 kPa. Okay, those are things you should have memorized. Okay, so 125 milliliters times the 0.974 atmospheres is equal to 1 atmosphere times V2. So I'm just going to multiply those two numbers. And so then V2 is equal to 122. Okay, so there's not much difference between the pressure here and here. Those pressures aren't very different. So it only decreases the volume a little bit. All right, that's Boyle's law. Boyle's law is very straightforward. Charles's law is much the same way. Oh, come on now. All right, so Charles's law, but this time instead of relating pressure and volume, we are going to relate volume and temperature. So Charles's law says that gas volume and temperature are directly related. Okay. So in other words, when the temperature increases, and the pressure stays the same, the volume has to increase. Okay, because you're increasing the energy of those molecules, so they're going to move more and more. So to keep the pressure the same, they have to expand. Okay. With this, we need to have a little discussion of the Kelvin scale and absolute zero. Okay, so you might make a little note. Absolute zero is one of your vocabulary words. Okay, it is the lowest possible temperature. It's the point from where we can no longer remove any heat. Okay, so on our Kelvin scale, it is 0 kelvins. Kelvin does not use degrees, it's just kelvins. So Kelvin and I'm gonna put a line to that so it's a 0 and not an O. Kelvin and Celsius are related scales. Their units are the same size, but there's no negative numbers on the Kelvin scale. So the Kelvin scale is equal to your temperature in degrees Celsius plus 273. Your book says 273.15. I don't care if you do the 15. We can just do 273 and call it good. Okay. It says in this book, they round off 273.15. They just round, they don't do the decimals. You don't have to do this. And so we're just going to take our Celsius temperature and add 273 to it to convert to Kelvin. So to do our math with this, the temperature has to be in kelvins. Okay. So if we were to graph Charles's law, we would have volume on the y, temperature on the x, and you would get a straight line. Okay. So as the temperature increases, the volume increases. Okay. The law mathematically, or as an equation, says V1 over T1 is equal to V2 over T2. So this time we're dividing. So don't let that mess you up. Really, it's still pretty easy because you can cross multiply and divide for whatever you're solving for. Okay. So we only have 2 practice problems for this that we're going to do together. So I'll work one and then you can pause, try the second one on your own because you should be able to do this math because you better have a calculator. All right, so let's get started. I'm going to switch colors. So we have our initial volume of 752 milliliters. We have our initial temperature of 25 degrees Celsius. I'm going to have to convert that though. So 25 Celsius, I'm going to have to add 273, which is going to give me 298 Kelvin. Okay. I'm again going to find the new volume at 50 Celsius. But again, I have to add 273 to that. So that is 373 Kelvin. Okay, so if the pressure is the same and I increase the temperature, then what happens to the volume of my gas? Okay. So we've doubled the Celsius temperature, but notice that that does not double your Kelvin temperature. Okay, and that's why we have to do this calculation in kelvins. You cannot do it in Celsius. You have to make that conversion. Okay, so we have V1 of 752 over T1, 298 Kelvin, is equal to V2, which we're going to find, over 373 Kelvin. I'm just plugging my numbers in. So I can cross multiply and divide. 752 times 373 divided by 298. And I would get that V2 is equal to 815 milliliters. Technically, you should have milliliters, in this case, neon. But as long as you have as long as you have units, I'm good. Okay, so pause the video, try this last sample problem, and then you can go on to the practice problems when you check yourselves. All right, so we have V1 25 is again 298 Kelvin at 100, so we're going to find V2 again. 100 degrees Celsius is 373. That's not right. Oh, I made a boo-boo. That was 323. Okay, couldn't figure out why those were the same number. Okay, 373 Kelvin. All right, so we do, this time the volume is in liters, but it doesn't really matter. 5.5 liters over 298 is equal to V2. So I just have to solve for that in liters. So 5.5 times 373, and then divide by the 298 gives me 6.9 liters of oxygen. Okay, so that is my final answer. Okay, so you need to work these practice problems. So it is a page front and back of practice problems. All right. Just covering these two laws. I will leave an answer key so that you can check yourselves and see that you're doing things correctly. Okay, but you're just applying Boyle's law and Charles's law today. Tomorrow, we will go on to the other two laws and do some practice there, okay? And then I think you have some labs next week after that. All right.